Okay, time is 12:30, so let's begin. Today we will start discriminant analysis. Probably talk a little bit about project number 2, that last problem that's on the project. On Thursday, we will have an out-of-class lab day to help you work on the project. I'll explain why I needed to change the schedule to do that shortly. So we're going to talk about discriminant analysis. So basically for the rest, pretty much the rest of the semester, we're going to be talking about the following scenarios. Scenario. Suppose you have n observations. And these observations come from known groups. In a statistical context, we can think of this as known populations. So it could be as simple as, let's say, the population of, let's say, athletes at this university, the population of non-athletes at this university. It could be as simple as the population of faculty, the population of staff, the population of administrators, the population of students. Okay? So multiple populations or multiple groups. We know what group each of these individuals are when we take that sample of n observations. And what we're trying to do is using, let's say, independent variables or explanatory variables or covariates, whatever you want to call them. We're trying to have those help us predict or classify the people into the correct groups. So this is different than what we saw with cluster analysis, where like we didn't know what kind of groups the goblets fell in. Here, we know the groups of every observation beforehand. Then once we develop out, you can say like a mathematical or statistical rule that says, okay, based upon what I see for these explanatory variables, we're going to predict that particular person to be in population 1, 2, 3, or 4, whatever. Once we get that rule, then what we can do is then apply it to a new situation and do prediction. So for example, well, I'm going to give you 3 examples where I've done this before. So remember that place kicking data set that we saw towards the beginning of the semester? So this is what the place kicking data looked like. We had 1,425 observations from an NFL season for every place kick that was attempted. The 2 populations, or 2 groupings, was the place kick a success or not? And that's what this variable good actually summarized. 1 for success, it was good. 0 for failure. And then what I've done in the past is let's use information such as the distance of the place kick, the wind, the type of field, is it grass or artificial turf? Let's use those kinds of information to try to predict, will this be a success or failure? We have 1,425 observations to help us make a mathematical statistical rule to make that judgment. Then, once we get that rule, imagine now that, let's say you're on the sidelines, you are a coach of an NFL team. You see your team's out there and they have an opportunity to do, let's say, a 40-yard field goal. It's not windy, it's on grass. Some other situations, in terms of these covariates, you could say too. Based upon that, then you use your mathematical rule. Imagine, let's say, you have your Surface Pro computer that they use in the NFL with you. You do some stuff, and it comes back, I predict a success. You can then use that to make a judgment about, should we go for the field goal or not? Okay? Here's another place where I've used these methods. So one time I was working with a wheat researcher, and in terms of the wheat kernels, get back to where it's at. There we go. So here we have some wheat kernels. And this researcher wanted to come up with an automated method to determine if these kernels could be considered to be healthy. Could they be determined to be sprout? You can imagine, let's say maybe it's a seed, maybe sprouted. Or the wheat kernel was scab, which means it's disease. And that's what these kind of whitish chalky ones look like. And so what he did was, I think we had like about 200 and some wheat kernels. And he looked at them all and made the judgment, was this healthy, sprout, or scab for each of them. Then he used this automated system that he developed that measured the kernel density, the hardness, the size, the weight, and the moisture content of the wheat kernel. Those are my explanatory or independent variables. Using that then, and knowing what the correct type of kernel, healthy, sprout, or scab, I developed a mathematical statistical rule to make that judgment, just based upon these measurements. And then what we wanted to do was apply now this new mechanism they developed to new kernels. So if he could get it right, then this would save a lot of time and give an automated way to make this judgment. Now, the last example that I've worked on was dealing with, I was working with a Department of Energy lab. And the Army wanted to determine a way to determine the contents of an unexploded artillery shell that might be on the battlefield. And the way to determine what was actually inside that shell, was it some kind of explosive? Was it mustard gas? Was it empty? What we wanted to do was develop a way to determine what was inside of it without making contact with the artillery shell. So you don't want it to explode. And so what we were trying to do was bounce some sound waves off the shell to make that determination. Now, when I was involved with this whole situation, I was working with some engineers. It was at the very, very beginning of this process. And so instead of using artillery shells, what we decided to do was use Sunny D juice containers. This is an actual juice container from our investigations, where we had some of these juice containers that were empty. So I got to drink the juice. We had some that had juice in it. We had some that had water in it, and some that were sand-filled. And so what we would do is we put these containers on a desk. We would bounce some sound waves off of it, make some measurements, and based upon those measurements, then we tried to develop a mathematical or statistical rule to judge what was inside the Sunny D juice container. Okay? So that gives you an idea of what we're going to be investigating now, essentially for the rest of the semester in terms of what our goals are. We're going to be talking about one of many different methods out there that can help us make this mathematical statistical rule. We're going to be talking about one right now called discriminant analysis. So we're trying to discriminate, I don't mean that word in a bad way, discriminate between the different groups or populations using a mathematical statistical rule. And what we're trying to do is something similar to what you would think of in like a regular old regression setting. So we looked at an example at the beginning of the semester where we were trying to use high school GPA to predict college GPA. Okay? Note that college GPA, you can kind of think of it as like a continuous response, somewhere between 0 and 4.0. Here, what we're trying to do now is that our response variable, or dependent variable, is actually categorical in nature. And one way that we can then deal with that to predict it is to use this technique called discriminant analysis. We will look at others as well. And in fact, so you can kind of call this almost like a classification method where you know what the groupings were beforehand. You could actually teach a whole semester on all the methods that are out there. We're just going to talk about some popular ones in this class. The reason why there's so many methods is because there's typically not one best method. So now to do this, we need to discuss something called a likelihood function before we actually get into talking about discriminant analysis. And looking at your backgrounds, you remember like that week number 1 quiz, you told me what all your backgrounds are. And one of the reasons why I want to know that is so that when I get to a place like this, I know what your backgrounds are. And I expect there are some of you who have not seen what a likelihood function is. So we're going to do a little bit of an introduction to it. Likelihood functions are used widely in statistics. They're used in conjunction with something called maximum likelihood estimation to come up with estimates of parameters. So now this comes from my what I posted over the weekend for this extra set of notes. I normally would do this set of notes in the factor analysis section, which we have skipped so far in this course. And so now I'm coming back to part of it. This material here that I'm going to be talking about actually comes directly from Appendix B of this analysis of categorical data with R book that I wrote. This is the book that I use for Stat 475 and 875, which is actually going to be offered next spring. Now, to help explain it, let's go back to one of the most simplest probability distributions out there, probably about the first or second one that you ever saw, and that was a Bernoulli distribution. So if you remember with the Bernoulli distribution, your random variable can be one of two different things, a 1 or a 0, where 1 typically means a success, a 0 means a failure. There's one parameter associated with the Bernoulli distribution. I'm going to call it pi, the Greek letter pi, and this represents the probability of success. Oftentimes when you see this introduced, it's maybe the letter P is used instead. Pi is often used in the higher level of statistics courses. So my random variable is going to be denoted by y. And I'm going to be formal here in my notation, where a capital letter means a random variable. So it can vary from, let's say, one instance of observing it to another. So y can either be a 0 or 1. And we'll relate this to a setting that we've just got done talking about, place kicking. We'll talk specifically about a field goal. A field goal can be a success or a failure. 1 is a success, 0 is a failure. And so then we can use some formal notation to define then the probability distribution, this Bernoulli probability distribution. So we use a capital P to always in statistics to represent the probability of something. So the probability that y is either 0 or 1 is what's shown here. Notice I use a lowercase y. So this is what you typically see in a more of a mathematical statistics course and some applied courses, where the lowercase version of an uppercase letter means an actual observed value. So all this little y's meaning for me is it's either a 0 or 1, but it allows me to say it in a general manner, rather than actually putting 0, rather putting 1 in there. And so then the probability distribution is pi raised to the y power, 1 minus pi raised to the 1 minus y power. And perhaps this is too simple, but we can go ahead and do it. Suppose this little y is actually equal to 0. Look what we get. 1 minus pi. Look what happens if this little y is 1. We get pi. So that will be an equivalent way to state the distribution. But by using this little y notation, it allows me to do it a little bit more compact. Okay. So the Bernoulli distribution can be used to model probabilities associated with making or missing a field goal, success or failure of a field goal, I should say. And let's say that we want to somehow estimate this parameter pi, this probability success parameter for, let's say, 40-yard field goals. So perhaps I go out to Memorial Stadium and I can't make a 40-yard field goal, but so I take one of our field goal kickers for the university with me out there, and I put the ball down on a tee from 40 yards. I say, okay, go ahead, and let's kick it a few times. how about we take a sample of 10 kids? Based upon that data, that sample, then I want to try to estimate what pi would be. And in a formal context, what you can do is form what's called a likelihood function to determine what are likely values of pi given your data. Rather than saying the word likely, I like to use the word plausible. What are plausible values of pi given whatever you have observed for your successes and failures for these 10 field goals? And so this is how the likelihood function is written out. I use an L for likelihood. It's a function, mathematical function of pi. Notice we have the word, notice we have the vertical line there. And you've seen that before in other places, in other classes. That means the word given. Just for emphasis, I'll write it. Think of like conditional probabilities. The likelihood function of pi given whatever I've observed my data to be. And just to be general here, instead of having 10 observations, I have little n observations. And all that the likelihood function is that you write out your probability distribution for each corresponding possible observation that you have. Notice I put subscripts on the y's now to indicate, okay, this is a y for the first time I kick a field goal. The 2 then represents the second time I kick the field goal. The n represents the nth time that I kick the field goal. So all I'm going to do is put that probability distribution in there all these times and multiply it all together. A more compact way to write this is to use product notation, similar to like summation notation. Product notation uses the uppercase pi. It's not connected to the little pi that we were using there. Just this is standard mathematical notation. So I take the product from I equal 1 to n of the probability of y sub I is equal to little y sub I. I plug in what that probability distribution is, do a little algebraic simplification, and this is what I get. So given what's in that exponent area of pi here, what would be a way to describe this in the context of our problem here? What does the sum of the y's mean? It's the number of
observation.
Not observations.
Successful attempts.
Number of successes. Yeah. So close, but yes, number of successful attempts. So if I observe something like this, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, the sum of the y's would be 4. That would be an example of data. Then in the exponent area of 1 minus pi, we have the number of failures. Well, let's say that I observe 4 successes out of 10 different observations that I've sampled. Let's look at what this mathematical function would be for particular values of pi. So if pi was 0.2, I get a likelihood function of 0.000419. Something I failed to mention is that the larger the likelihood function is, the more plausible your value of pi is. Suppose pi is 0.3. Notice how this increases. Pi of 0.35. Notice it increases. And in fact, it keeps on increasing all the way up to pi of 0.4. And then after 0.4, it starts going down. We can actually plot then what the likelihood function looks like this. And again, how the likelihood function works is that the more plausible the value of pi is, the larger the likelihood function will be. So then what's the most plausible value of pi here? 0.4. In statistics, we call this most plausible value of pi then the maximum likelihood estimate. And so what we've just done here is what's called maximum likelihood estimation. There's a lot more that I could go into, but we don't need some of this extra stuff that's now on page 4 and later of these notes. So I'm basically going to stop for now in these notes and just say that if you want to investigate a more mathematical way that applies stuff in Calc 2 to actually find what that maximum likelihood estimate is, you can take a look at how to use derivatives and stuff to find it. But the key thing is this. The larger the likelihood function is, the more plausible your result that you put in there for pi is. That's the key. Okay. So now we go back to discriminant analysis. We're going to look at a special case where we have just two populations, or again, you can think of it as two different groups. Do note that there are a few places in these notes where I colored in red because I wanted to add and actually write down here the mu and the sigma should have been bolded. That was my error because we were talking about vectors and matrices. So we have two populations or two groups. And to help us conceptualize this, suppose both of these populations can be characterized by a multivariate normal distribution, but different multivariate normal distributions. So they have potentially different means and different covariance matrices. Now, you've all looked at situations like this before in your very first stat course. Remember doing a hypothesis test for is mu1 minus mu2 equal to 0 versus not equal to 0? It's the same thing, except now we have multivariate normals instead. So instead of working with one variable, you're now working with up to p different variables. Suppose x, then notice that's bolded, denotes an observation from one of these populations. And the ultimate goal of essentially what we're going to be doing for most of the rest of the semester is that we want to be able to predict, or let's say classify x as coming from population 1 or population number 2. So let's look at ways now we can do that. 4 different, let's say, what's called discrimination rules relative to discriminant analysis. And they all are interrelated to one another. The most general of these rules is called the likelihood rule. That's why we were looking at the likelihood function. And so now in this context, for this situation where the populations are characterized by multivariate normals, we can write out 2 different likelihood functions. One has mu1 and sigma 1. The other one has mu2 and sigma 2. And also, I should have changed the notation here. This little notation here is just a quick little way. I got the notation from another book, so blame that other book. This little notation where I'm using that capital pi again, some people like to use it to represent particular populations. It has nothing to do with the product notation that we saw before. It's just a way to say population 1, population 2. And so, again, our goal is to figure out which population X comes from. So we can look at the 2 different likelihood functions. The likelihood function that is larger then corresponds to the most, let's say, plausible population for X. That's it. So if the likelihood function for population 1 is greater than for population 2, choose population 1 for X. Otherwise, choose population 2. That's all. That's all there is to it. Now, as I said, there's 4 different rules. Rule number 1 is the most general. We typically actually won't use that rule. 2, 3, and 4 all rely on a particular simplification. And that is, suppose the covariance matrices are equal to one another for the two populations. We'll look at how to get rid of that simplification later. But it's easiest to start with this simplification. All 3 of these remaining rules have it. To simplify your lives, I decided I'm not going to talk about rule number 2. So that's why I have it all blacked out. You're not responsible for it. This used to be what people would focus on in a class like this. I don't think it's worthwhile because it's actually the most difficult of the rules to understand. Also, R doesn't provide a good way to, let's say, it implements it, but it implements it in kind of a weird way. And so that's why I don't think it's really worthwhile. And so I decided when I was going through my notes yesterday that, hey, let's save some time and not even talk about it. You're welcome to take a look at it underneath the black after class, but you're not responsible for it. Instead, we're going to focus on rule 3 and 4. This 3 one is called Mahalanobis distance rule. Mahalanobis is a particular person. He's a famous Indian statistician, and he has some things named after him in statistics, and including this one here. This is how it works. Again, assume the covariance matrices are equal to one another, and so you could just call it sigma as the covariance matrix that we have. And what we're going to do is look at the distance that X is from that population mean, either population 1 or population 2. That's why I have an I there to be general. We're going to look at the distance. But we understand that variables can have different variability. So how about we take that into account by also including sigma in there as well. So we take X minus mu sub I, transpose that, take it times sigma inverse times X minus mu sub I. So we've seen something like this before. It looks very similar to that Euclidean distance. The difference is that we have sigma in there instead. Also to relate it to something that you've seen before, suppose P was 1, meaning that we have just one variable. That's what it simplifies down to. Does that look familiar? Yeah. So it's like almost like a multivariate version of that. You know, the distance that X is from you, taking into account the variability. Looks like a z-score. So we get D1, the distance X is from population 1. We get D2, the distance that X is from population 2. And we compare these two distances. If the distance for 1 is smaller than the distance for 2, predict then that observation X came from population 1. That's it. It's closer. It makes sense. It's closer to that mean, taking into account the variability. Otherwise, if D2 is smaller, well, predict or classify that observation into population 2. That's all there is to it. Very simple. So here's a plot that helps demonstrate this. Suppose we have two variables, x1 and x2, and let's say that they have exactly the same variability. Let's say that these variables actually end up being independent of one another. And what I've done is I've drawn where mu1 would be, I've drawn where mu2 would be, and I put a contour there as well. And we see that we have this one let's say observation X, let's call it X sub 0. We can see it's closer to the mean for mu1, so we would classify that X to be from population 1. Okay. The fourth way, very closely connected to the distance rule, but perhaps it gives you something that's a little bit more interpretable. It gives you what's called a posterior probability of X, where, and we have to be careful, it's not exactly a probability. So those of you who've had some Bayesian classes, be careful. It's not exactly the same. The probability of, let's say, being from population I, given what the value of X is, that probability is equal to, use the exponential function, -1/2 times that distance, divide by the same quantity, but now for both distance 1 and distance 2. And notice how the numerator has to be always less than the denominator, right? With the exponential function, can you get any negative values? Nope. So I'm always going to have a positive value here where the numerator is greater than the denominator. So what's the numerical range of this quantity? Between 0 and 1, just like a probability. Okay? And so if this posterior probability for being from population 1 is greater than the posterior probability for being population 2, predict population 1. Otherwise, predict population 2. That's it. So what this is basically doing is just rescaling D1 and D2 to give you a number between 0 and 1 so you can make a judgment of how much evidence there is, population 1 or population 2. That's it. It's just a rescaling of the D's. Any questions about that? Now the word posterior comes about because basically we are calculating a probability after observing what X is. Post. That's where the name comes from. Now, in the end, of course, mu sub I and sigma I are not ever going to be known. So what do? We replace the unknowns with their estimates when we do these calculations. Now, what happens, though, when we assume that sigma 1 is equal to sigma 2? Well, then we do something very similar to what you had in your very first stat course, again, when you did that hypothesis test of mu1 is equal to mu2, or mu1 minus mu2 is equal to 0. Remember coming up with something called like a pooled estimate of the variance? We're going to do exactly the same thing here, but a multivariate version of it. This is what it looks like. Compare this expression to what you had when you were doing that hypothesis test of mu1 minus mu2 is equal to 0. It's just a multivariate version of it. That's it. So the sigma hat 1 is the estimated covariance matrix, just like how we calculate normally. Now for population 1, sigma hat 2 for population 2, N1 is the sample size from sample 1, I'm sorry, from population 1, and 2 is the sample size from population 2. So right now we're just focusing on 2 populations, but eventually we'll get to a case where we have 3 or more populations or groups. So how would you adapt these rules? You know, think of it in terms of, probably the easiest way to think about it is, well, but let's talk about the Mahalanobis distance rule. What do you think you would do? Suppose you have 3 populations. Calculate 3 distances. The distance that's the smallest corresponds to where you're going to predict that observation into. What happens to posterior probabilities? Well, if you have 3 populations, you're going to have 3 posterior probabilities. You predict that observation to go into the population that has the largest probability. That's it. Now, something that's going to be very, very, very important to us is to measure how good is this mathematical or statistical rule at predicting. Ideally, we would like to have a 100% success rate for predicting population 1, 100% success rate for predicting population 2. Guess what? That usually doesn't happen. But we like to estimate how good we're going to do. Or let's reverse that and say, let's estimate the probability of misclassification, the probability of making an error. So, there are 4 ways to estimate that probability. The first way is the best way to do it. So let's say that I developed, let's say, a rule for, which one do we want to use? Oh, we'll do the field goal kicking again. So let's say, so not just the 40-yard field goals that we were talking about for that simple example. Let's say for any distance field goal, for any wind conditions, for any field conditions, and so on. I take a sample, I make a statistical rule based upon using maybe like the Howell-Knowles distance rule. Now, I want to determine how well this rule is going to work. The best way to do that is to go out and take another sample and test it out. Where in that sample, you are actually tracking, did I have successes or failures? That would be the best way to do it. What's a potential problem with doing something like that? You don't have to think of it in terms of football. Think about any situation where you take a sample, you estimate a model, and you want to try it out. So you go out and take another sample and test the model out. What's the problem with doing that?
Is it that you assume you're sampling from the exact same population?
Well, that's what you're hoping for. Yes. That wasn't the answer I was looking for, but I will tell you that corresponding to this here, we developed a rule that using, I think it's method 3 here, that we saw was doing very well. Then when we actually tried it out on some new data, it did horrible. And the problem was dealing with the population. In terms of our experimental conditions, we were not controlling them very well. So essentially we had different populations. So I'm actually looking for a different answer here. What's the problem with going out and having to collect another sample? Perhaps this might be a little bit too obvious. Suppose you're having to pay for it. Okay? It's going to cost more money to go out and take another sample. It's going to cost more time. And so that's why often in practice, it doesn't happen. So what can we do instead? Well, how about you take your one sample, and before you do anything else with it, you say, okay, how about we take maybe 50% of the data, put it over here to the side. Then we take the remaining 50% of the data, we try to develop this new statistical mathematical rule upon it. And once we get that rule, then we apply it to that data that we put aside. That's a good way to do it. But what's the problem with this method?
You have less data to train on.
Yes, you have less data to train on. Train is going to be a word that we're going to use in terms of we are building the model or the rule on some data, but now, based on what I just said there, it's half as much of the data. The more data you have, you would expect the better the rule, the better the model will be. And so that's a problem. So method number 3, we use something called resubstitution, where what we do is we develop this statistical mathematical rule on data, and then we try it out on exactly the same data. What's the problem with that? Well, potential bias. because that rule is going to perform probably the best on the data that you developed it on. Depending upon the situation, it's not maybe as bad as it sounds. We'll talk about examples coming up, but that's definitely a problem. The last way is to use something called cross-validation. There's different ways to do cross-validation. We're going to focus on one here called the leave one out method. And this is how it works. Suppose you have a sample of, let's say, a sample size of 1,000 for something that you're working with. Remove, let's say, observation 1 from the data set. Develop your rule, your statistical rule for prediction on the 999 observations remaining. Then go try it out on that one observation that you've taken out. Determine if you were a success or failure in terms of, did it work? Did I predict correctly? Put observation number 1 back in the data set. Then take observation number 2 out. Develop your rule, your method. Predict observation 2. Determine if you were a success or failure in terms of the prediction. Then you keep on doing that process over and over and over again, so that every single time you're using 999 observations and always trying to predict one. And then after you've done that for all 1,000 times, then you can, so essentially you're doing this 1,000 times, then you look at, well, how good was your method? What was your overall success rate? So what's the problem with doing that?
Time consuming?
Yeah, it can be time consuming, depending upon what you're doing, depending upon how many observations you have. Okay? So that's called a leave one out method. This is a form of, in statistics, what we call jackknifing. We have very few interesting names in statistics. This is one, jackknifing. There are other ways to do this. So you could do what's called a 5-fold cross-validation, where instead of taking out one observation, suppose you take out 20% of your observations. Develop the model on 80%, try it out on the 20%. Put the 20% back in, take out another 20%, and so on. That's another way to do it. We're just going to focus on the leave one out method here. Now, what it often comes down to is that you're often left with using resubstitution or cross-validation. You know, we saw problems with the first method, the second method. And if you're given the choice between the two, cross-validation is the better approach. It will give you, let's say, a closer to being unbiased estimate of what your error rate, your misclassification rate is. And so because of that, then, cross-validation will typically result in a higher misclassification rate than resubstitution. Doesn't mean that there's a problem with the method. It's just is giving you a better estimate. Okay. So now let's go back to the place kicking data set and try some of this stuff out. With the place kicking example, I actually do have a separate, let me make sure I'm using the same term again. I actually collected the data myself. I actually, at the very beginning, split the data into 2 different parts. So I have one part that I'm going to use to come up with this discriminant rule, and then I have this other part that I'm going to try it out on. The actual way I split it, I didn't do a 50-50 split. I ended up doing an 83%, 17% split. If I were to do it again, I would do 50-50. But at the time, I did it this way based upon some recommendations that I don't really think are valid anymore. You will see people recommend 80-20% splits or 50-50 splits. I think typically I tend to go towards a 50-50 split more often nowadays. Let me also make sure that I define a certain terminology here. Okay. Yeah, let me come back here. So corresponding to what was said earlier. So when I do split the data set into two, the part of the data that I use to develop this discriminant rule, the statistical rule, is often referred to either a model building data set. Some people will call it a training data set. Those are typical names that are used. The word training means you're training this method on some data. Now, the data set was, let's say, put aside, that you're going to test the method out on, is sometimes called a holdout data set. Sometimes it's called a validation data set. You want to validate your procedure that you're developing. Some people will call it a test data set. Some people will call it a calibration data set as well. So be familiar with those terms. So now with the method that I've introduced, it relies on a multivariate normal distribution assumption. Do you think we have data that comes from a multivariate normal distribution here? Yes or no?
So like really all the variables have to be converged?
Yeah, I mean, we talked about, earlier in the semester, how do you make the multivariate normal distribution, how do you validate it, essentially? And we said it wasn't difficult. It wasn't difficult. It was difficult. But what we see here is that we have some data that's actually binary. Grass versus artificial turf, for example. That can't be multivariate normal. So you might be wondering, why are we talking about this method applied to this data? Well, this method often works very, very well, even without that assumption. That's why. And in the grand scheme of things, the way that I approach problems like this, I will try discriminant analysis. I will try another method, and I will try another method. And I look at these methods, and I look at the misclassification rates. The method that gives me the best, meaning the lowest rate, that's the method I typically will go with. Again, as I said at the very beginning, no one method is always best. That's why it's often good to try out multiple methods. So to do this in R, there's a function called LDA. The DA stands for discriminant analysis. The L corresponds to a specific type of discriminant analysis that we're using, and I didn't introduce that yet. It's called linear discriminant analysis. Once we take a look at another discriminant analysis method called quadratic discriminant analysis, then it'll be easier for me to say, why is this called linear? Why is this called quadratic? So stay tuned. So here's what my data looks like. I've read it into R. And, before you do one of these methods to decide, or to develop this statistical mathematical rule, it's always good to take a look at your data using some of the methods that we've talked about already. Do some plots. Do principal component analysis. So that you can get an idea of, will this work? Is there something here that will help me determine, is this place cake going to be a success or a failure? And so what I did here is I did principal component analysis. Of course, I used the correlation matrix. And let's actually take a look at this. So how many principal components do you think will be appropriate for this data set?
Four or five.
Probably at least 4. Four explains 70% of the variability. Notice the eigenvalue for 4 is greater than 1. When I get to 5, I'm now over that 80% threshold. This is not a set threshold that people have. I like to get 80% or more, but I know oftentimes I can't. For that 5th principal component, of course, I do have an eigenvalue less than 1. Can I still look at 2 or 3 principal components, though? Only? Yeah, you can still look at it, look at it graphically. You just have to have in the back of your mind, you might be missing some information. So let's look at 2 and 3 principal components. This is what we get. And notice what I have here in red. I should have included a legend. I don't know why I didn't. The red is the successful place kicks. The black is the failed place kicks. So we see some banding there. Why do you think we have this banding occur?
Is it because of like the binary data? So like a lot of them are going to have like exactly 1 or exactly 0.
Exactly. It's because of the discreteness that we have in our data. So this isn't saying anything's wrong. It's just because of the nature of your data. Now notice, it seems like as for principal component number 1, the farther we get to the right, the more blacks we have. So for those of you who are football fans, what do you think principal component number 1 is representing? Distance. Let's go back. Notice you also have PAT there. PAT is binary, where is it a field goal or point after touchdown, and this PAT is closely related to the distance. If you do have a point after touchdown, it's often a distance that's, at least with this data was collected before the current rules were out there for the NFL. These PATs were 20 yards. So that's what we're seeing. That's why we have the blacks getting more prevalent as PC number 1 increases. You might want to be, and here's also a 3D plot as well. Just to show you, to help you understand the banding. So I colored the points corresponding to if it was a PAT, which is blue, or if it was a field goal, which is green. You can see the effect of that. You can also see the effect of the field variable as well. And to be honest, unless I have it in there, I don't remember off the top of my head. You can see it in the program. Blue would probably be, well, it's either artificial turf or grass. I'm sorry, I don't know off the top of my head. Okay, let's get to the main point here. What we see is we do see a little bit of separation there in that plot, which makes us think, okay, maybe I might have some success in differentiating between the successes and failures for a place kick. So let's go ahead and do discriminant analysis. So our function LDA is in a function called mass. I think we've seen the package before, mass.
Yes.
Okay. Modern applied statistics with S. LDA, and then we have a formula argument that's very similar to what you have for a regression model with the LM function. Good is our variable that is our grouping variable or our population variable. You can think of it almost as a response variable. It's not exactly, at least the way that we conceptualize everything. So we have good there, which is 0 or 1. And then we put in the corresponding explanatory variables. The data is in place kick. I have an argument called CV. That stands for cross-validation. Do I want to do cross-validation? Typically, you always do, and the default is true. I only put false here so I can show you what happens and to help explain some stuff. And then I have another thing called prior. I'll explain that more coming up. But what this basically is saying is that what's the what would you expect the probabilities to be for that would be in the failed group and the success group in terms of, I didn't word that very well. What proportion of the items in these let's say if you were to combine the populations, what proportion would be from the good group, which would be from the failed group? Sorry, success group or failure group. And by saying 1 divided by 2 and 1 divided by 2, basically I'm saying 50% are from the success, 50% are from the failures. That is not true. I'm only putting that there for now to illustrate some stuff. So make a note, if you're taking notes, that what I'm doing here is typically not how you want to implement the LDA function. So, I understand as a student, you want to quickly apply something. So you see the very first time the LDA is used, and you're going to copy and paste that code to your own program, and you're going to apply it exactly the same way. Don't do that. I'm only applying it this way to help demonstrate some stuff coming up. So I put all the results, and I'll explain prior more coming up. I put all the results into an object called DA1, for the lack of a better name. And this is what we get when I just type DA1. We have some summaries. So for example, we have group means. All that corresponds to, remember, good equals 0 is failure. Good equal 1, success. All this says, okay, for a distance of, the average distance for successful place kicks is 25 yards. The average distance for failed place kicks is 40 yards. That's all that that's saying. There's some other information displayed here as well that is not going to be of interest to us. This corresponds to that second discriminant rule. Whenever you use a function for the very first time, one of the very first functions that you want to implement right after that is the names function, so you can see what is returned to you in a list. And so if I say names DA1, we have some information being displayed here. So for example, all those means that we got above are in there. Oops. We can also see what's the class of DA1. It happens to be LDA. And then we can see what generic functions are associated with objects of class LDA. The main thing that will be important to us is this thing called predict. Because what that will do then, it will tell us for every single observation in the data set, should I predict this to be a success or should I predict it to be a failure? So let's actually implement that. So if I say predict object equal DA1, put the results into pred.resub. The reason why I use resub there is because this is using resubstitution. Again, I can say names for pred.resub. You can see the information that's in there. In particular, if I pull out the posterior component of the list, here are all the posterior probabilities. So for observation number 1, what would you predict as the population or the grouping? Success, because it has a higher posterior probability. And we can see for so many observations at the very beginning, it's a high probability. If I were to extract the class component of this object, then you actually have the 1s and the 0s for the predictions. The X component, don't worry about. That's why I blacked it out. Okay, so we talked about the CV argument. We talked about the prior argument. I blacked out some more. And normally I would have actually extracted this from the notes before you got it, but I just made a last minute decision about, let's just remove it. It's not worthwhile to talk about. So this coefficients of linear discriminants, just to emphasize this, it corresponds to this linear discriminant law that you're not responsible for. So then we also talked about the predict function as well. Okay. So what we can do is how about we try to replicate some of these calculations. That's why I chose to do this LDA in a certain way, because it will make it easier to help you learn how some of these equations work. So to begin with here, let's take out observation 1 from the data set. And notice I have a -9 there as the column. That just removes that good variable from what I'm extracting. And in order to get the data into its correct form, I needed to tell R, hey, treat this as a matrix. So I use the as.matrix function. Also, R, I want you to transpose it so that it is a column vector. And so that's why I use the T there. And there's observation number 1. Next, I need to actually extract those observations that were coming from population 1. So I go back to my good variable. I do == 0. Does someone know what that does? It's a logical comparison. What it does, it compares each of the good values. Is it a 0 or is it a 1? And so notice you see falses, you see trues. So notice the very first 6 observations are 1s. The very first 6 here are then falses. So when I put falses and trues in terms of the row index of place kick, what's going to happen? It's only going to return the true rows. So if I run this segment of code and do head pop 0, I end up, well, trust me, if good was there, it would actually be all 0s. Let me just do it off to the side. There. Okay. So it's a common way that people actually extract portions of a data set corresponding to some kind of logical condition. So I form the sample, I get the sample from population 0, the sample from population 1. I find the sample size from population 0, the sample size from population 1. I find the estimated covariance matrix from population 0, population 1. I find that pooled covariance matrix. And to be honest, I think we're running out of time. I was hoping I would get through all this, but it's just not going to work because this is actually kind of complicated. So what I will do then the next time that we actually meet here is actually go through some of these by hand calculations, or what I would call by hand calculations, that basically put all the equations I showed you, puts them into an R context, okay? Let me come back here. So today, I will have office hours. I forgot to delete that, sorry, in my office after class. Thursday will be an out-of-class lab day. Next Tuesday, we will continue with discriminant analysis. We will get back to project number 2. Looking further ahead, Project number 2 is due Thursday, November 13th at 5 p.m. I thought I was going to get farther today, farther than what I did. And so I'm going to, again, still say that's a tentative due date because of that problem number 3. You still don't have enough background to quite do problem number 3. If you read a little bit more in the notes, you'll be able to actually get it all. But we didn't get as far as I wanted to. Test number 3 is Thursday, December 14th. Are there any questions? Okay, that's all for today.